Hello, my name is Ethiopia Ngusi. I work at the University of Turku. This demo presentation is part of the work carried out by University of Turku and TTS in Prystine project. In demo 2.3, we are working on fail operational environmental perception for heavy-duty truck by focusing on data fusion and fallback mechanism. The aim is to implement fail operational and secure controller that enable assisted automated driving for heavy-duty truck. This will be achieved through deployment of several sensors on the truck, development of middleware that detect and contain security incidents and faults, and sensor fusion, which is aware of sensors and data trustworthiness. We have 3 use cases for this demo. The first one is safe departure and safe stop. As you can see it here, for safe start or safe departure, the driver has to monitor all the surrounding environment and track those objects' movement. So here we have deployed using the track maker, we simulated safe start and safe stop. And as you can see here, we have the radars at the back of the truck and at the side and also at the front. We have also radar at the corners and also camera. So in our project, we use this 24 gigahertz radar and several types of cameras. So here you can see that it stops because the bus is about to leave, and then it starts again safely. And this is the second use case, which is right turn. And for the truck with trailer, it's maneuvering is challenging in case of right turn, because if the maneuver is not precise, the trailer may occupy the oncoming lane, which may cause head-on collisions. And also, it is very challenging where if there are those pedestrians or cyclists who are crossing, especially if there are some greenery areas which makes it difficult for the driver to see the pedestrians. And the third use case is lane change in a highway. And this lane change in a highway in severe conditions, especially in Finland when the visibility is very poor and the roads are slippery, will make it very challenging for safely changing lanes if the driver do not have the accurate surrounding environment perception. So here you can see that the driver changes the lane to the left with the help of those perceptions. So the controller has the block level depiction of the controller, and its components are here, as you can see. So the key elements is we have the middleware on top of the operating system, which integrate the firewall, access control mechanisms, and also distributed monitors, which monitors faults in hardware and software components. We have the sensors here, the intrusion detection system, the fusion, which also takes into account the trustworthiness of the sensors and their data, and of course decision and control, which allows for the actuation. So in our work, we have used a hardware platform which is authorized, certified for vehicle use, and based on this Intel Core i7 and NVIDIA GPU. It has several interfaces and also inbuilt GPS, GLONASS, and Galileo. So the trust model is one of the key contributions of our work, and the trustworthiness it evaluates. The trust model evaluates the sensors and sensors data by considering sensor-specific limitations which are available from in their datasheet, but also testing them in different conditions, and also taking into account the environmental conditions, weather, and system integrity if there are any security incidents. So we have the source trust, which evaluates the environmental conditions, the integrity of the data, and the identity. But also we have the data trust, which evaluates the consistency of the data, the information, and the reliability. And then we have also enhancing parameters such as source detection, corroboration, and prediction accuracy. And these values are the outputs of the trust model will be used to adjust the weights of the sensors during the data fusions in order to reduce the negative impacts of untrustworthy sources. So here we have simulation of the trust model emulating the BugSense 9000 radars, which data collected from the BugSense radars that are installed on the heavy-duty truck. And then its motion tracking, field view, object count are evaluated from the radar data. And on the left, a real-time breakdown of parameter categories are evaluated, including sensor-specific factors, as well as operational, environmental, and security-related parameters. The trust model is implemented in Python using the ROS environment. Of course, we also developed intrusion detection system for CAN bus data for protecting from various, for protecting those internet data communication from cybersecurity attacks. And the intrusion detection is based on CAN bus ID sequence, and it is part of the fail operational middleware. So the vertical distance between the green and the red shows corresponds to the IDS idle time, and with maximum bitrate and full usage, the IDS decision is often available before the whole message is read. And this evaluation of the IDS is made based on the data collected by TTS track, the radar data, and also the openly available OT-IDS dataset. As you can see here, the memory requirement is low, and it also has more than 95% of true positive rate. And finally, we have also object detection from the camera data of the TTS track, which is implemented used by running this YOLO version 3 on the hardware on the controller. And as you can see here, we have the pair of values which indicates location and confidence value. Thank you.